This is part 2 of the piston cylinder with 2 sets of stops problem. In part 1, we solved for the amount of work that the water did on the system. In part 2, we are going to solve for the amount of heat that was added to the system in order to turn the saturated mixture water into superheated vapor. This is a continuation of part 1. So if you're interested in how to find the different states, and to figure out the phases that the water is in those states, please go watch part 1 because this is a continuation of that video. So let's go ahead and get started. So we are trying to find the amount of heat added to this system. So we know that from state 1 to state 2, some heat was added. And then from state 2 to state 3, more heat was added. And then from state 3 to state 4, more heat was added as well. So we need to go ahead and find Q from 1 to 2, to 2 to 3, and to 3 to 4. Great. So we know that this is a closed system, right? There's no mass coming in or out of our boundaries. In this case, our boundaries of the system is our piston cylinder. So we know that it is a closed system. Closed system. And for closed systems, we can use the following equation to figure out the amount of heat using our thermodynamic tables, our steam tables, right? So right now we're going to try to figure out 1 to 2. And the equation that we use for closed systems is Q minus W is equal to delta U. So heat minus work equals change in internal energy. So we go to state 1 and state 2, and we see that from state 1 to state 2, there was no work. And the way that we can tell that there's no work is because the piston isn't moving, right? So if nothing is moving, no work is happening. So we're able to cancel out that from our equation. So we don't have to worry about it anymore because there's no work, no moving pieces in our system just yet. So our equation simply turns into Q is equal to, let's write it over here. Q is equal to change in internal energy, or we can even write it out more and say that Q is equal to U2, or the internal energy in state 2, minus the internal energy in state 1. Great. And internal energy here is going to be in kilojoules, just because I did not mention that. You're not going to be able to see the units in the tables here, so just kilojoules. Alrighty. And also, another type or form of this equation that we're actually going to use more often is going to be that Q is equal to the mass times U2 minus U1. But these U2 and U1, these are specific internal energies. These are specific internal energy. And those are the terms, or those are the internal energies that are tabulated in the back of your textbook. They're not tabulated as kilojoules. They're tabulated as kilojoules per kilogram. So those are the units we're usually going to work with. And we find those using our tables. So let's go ahead and start finding U1. So find U1. So, right, U1 as in specific internal energy, the internal energy in our state 1. In our state 1, we know that it's a saturated mixture, as we found in our last video. And we know that the specific volume is 0.835 meters cubed per kilogram. Go ahead and write that down. Specific volume is 0.835 meters cubed. And we know that the temperature in state 1 is 100 degrees Celsius. Great. And in order to figure out the internal energy, right, our U's, we need to know the quality of it. Since it's a saturated mixture, we need to find quality. And so for a saturated mixture, the internal energy is going to be calculated like this. U1 is equal to the quality of UV, internal energy of the saturated vapor, plus 1 minus the quality of U of this saturated liquid, like that. And the way that we find quality is with the equation of quality is equal to specific volume, or any other tabulated info that you have. In this case, we are given the specific volume. We know the specific volume. Sometimes you won't know the specific volume, but you'll know the specific internal energy or the specific enthalpy, and that's another way that you can solve for the quality of your system. But in this case, we're giving specific volume, so we're going to use the specific volume in order to find the quality. Great. So in order to find the specific volume of the liquid, of saturated liquid, and the specific volume of the saturated liquid vapor, we're going to go ahead and look at our tables. We're going to look at where the temperature is at 100 degrees Celsius. Again, this is going to be the table for saturated liquid vapor mixtures in your textbook. We look at that, 100 degrees Celsius, and we see that our specific volume for the liquid is right here, and we see that the other term that we need is right over here. So I'm going to go ahead and write them to the side. So VL is equal to 0.001044, and then our volume of the liquid vapor, our specific volume, is 1.67185. And then for fun, we're just going to also say what the specific volume is for the saturated vapor, which is going to be 1.67290. Great. And then we find quality. We use the formula. So it's going to be our specific volume that we have already found of 0.835 minus 0.001044 over 1.67185. Plug that into a calculator and get 0.4988. So that's our quality of our saturated mixture. Great. Now we plug it in to our formula over here to figure out the internal energy in state 1. So we're going to do U1 is equal to the quality, 0.4988 times our internal energy of the vapor phase. So again, we're going to use our tables. So we see that UV is 2,506.50. It is kilojoules per kilogram. And then our UL, or our internal energy of saturated liquid, is going to be 418.91 kilojoules per kilogram. So UV is 2506.5 kilojoules per kilogram plus 1 minus our quality times the UL, so 418.91 kilojoules per kilogram. We plug that all into our calculator, and we get that the internal energy, or the specific internal energy of our system in our state 1 is going to be 1,460.1999 kilojoules per kilogram. So we know the specific, our internal specific energy, right? Great. So that's part 1 kind of everything we have to do. Because in order to find the heat added to the system, we need to find U2 and U1, right? So we found U1, let's go ahead and find U2. Or find U2. And again, it's going to be the specific internal energy. Okay. So in state 2, we see that it's a saturated mixture. Great. So again, we're going to use our saturated mixture tables. So our saturated liquid / vapor mixture tables. I don't know, whatever their name is, whatever the name is in your textbook. So we know it's a saturated mixture. So that means we're going to have to find quality. And we know that we're going to have to find quality, and we know the formula for quality is going to be quality is equal to specific volume in state 2 minus the specific volume of the liquid mixture, or the specific volume of the liquid mixture phase, I guess, divided by the specific volume of this LV. And we know that the formula to find U2 is equal to quality times UV plus 1 minus quality UL. Great. And again, these are all specific internal energy terms, right? So it's always going to be over kilograms when we're using our tables, or at least when I'm using my tables. Depends the units on your tables. We know that the specific volume in state 2 is 0.835, and we know that our system at point 2, or phase 2, is, or state 2 I mean, is at pressure of 200 kilopascals. Great. So we look for where it says 200 kilopascals in our table. And in order to find quality, we need this guy and we need this guy. So we plug that into our formula. Quality is equal to specific volume minus specific volume of the liquid divided by the specific volume of the liquid vapor. We plug in all of our terms, so 0.835 minus 0.001061 divided by 0.88467. Plug that all into a calculator and we get 0.9427. So in state 2, we have a higher quality saturated mixture, which makes sense because we added heat to it, right? So it's acting less like a liquid and it's acting more like a vapor. It's closer to becoming a fully saturated vapor, or even it's becoming close to becoming a superheated vapor. Great. After we find the quality, we find the internal energy of state 2. We know the quality, we know the formula, so we need to find UV and UL. And UV and UL is really easy to find. UL is right here, and UV is right there. And now we plug those into our equation, and we finish this up. So U2 is going to be 0.9427 times 2529.49 kilojoules per kilogram plus 1 minus the quality, 1 minus 0.9427 times 504.47 kilojoules per kilogram. So our specific internal energy of state 2 is 2,413.4564 kilojoules per kilogram. Great. Finally, we can find the heat added to our system because Q is equal to M times U2, and these are specific, U2 minus U1. We know what the mass is because it told us in our problem statement. The mass is 1 kilogram. So I'm going to go ahead and plug everything in. So mass is equal to 1 kilogram. U2 was 2413.4564 kilojoules per kilogram minus U1, which was 1,460.1999 kilojoules per kilogram. These kilograms cancel out, and we get, after plugging it into a calculator, we know that the heat added was 953.2565 kilojoules. So this is the heat added going from state 1 and going to state 2. Great, perfect. But that was only one part. We also have to find the heat added from going to state 2 to state 3, and the heat added from going to state 3 to state 4. Great. So let's continue. So now we do state 2. To state 3. Since it's a closed system, we use the formula Q minus W is equal to delta U. From state 2 to state 3, the piston does move, so we have work involved. Great, so we can cancel that out. We know the state, and we know the type of the phase that it is in state 2 and state 3, so we will be able to find U3 and U2. So U3 minus U2. I'm going to go ahead and let's go ahead and add W on both sides. So Q is equal to, remember, U3, U2, if we want to use our tables, because our tables gives us specific internal energy, we're going to have to multiply it times the mass. So mass, U3 minus U2 plus W. Again, we multiply times mass because our table gives us our internal energy in terms of kilojoules per kilogram. So in order to get rid of those per kilogram, we have to multiply it times the mass. And we added work on both sides so that we can solve for Q. Luckily for us, we solved for work already. We know what the work was. So we found work over here, and work was 1.2 kilojoules, right? So that's something we won't have to deal with because we know that work is equal to 1.2 kilojoules. Great, now we just have to really find U3 and U2. Great, so let's go ahead and start finding that. We know, oh, and also we know U2 because we found U2 in our earlier calculations. We know that U2 is equal to 241. Let's write that again. We know that U2 is equal to 2,413.4564 kilojoules per kilogram. So that's great. We only really have to find U3. That's the only thing we don't know in order to find the heat added at this point in our system. So we need to find U3, and we know that at state 3, it's a saturated mixture. And since it's a saturated mixture, we know we're going to need quality because in order to find the specific internal energy, the formula is equality UV plus 1 minus the quality UL. Great. At state 3, our pressure is 200 kilopascals, so that's going to be key in order to find things on our steam tables or our saturated mixture tables. And we know that the specific volume at state 3 is 0.841 meters cubed per kilogram. And if you're interested in finding out how we got those numbers, please watch part 1 because I'm not going to go over it again. Formula for quality is the same as always. I'll write it again. Great. We're going to go ahead and find the specific volume of this state when it's a liquid, so VL. Still, it's the same as last time, right? So VL is still the same as it was for U2 because we're still at the same pressure. So since we're at the same pressure, UL, UV, as well as the specific volume of the liquid mixture and the specific volume of the liquid vapor mixture, it's all the same as it was in our last, what we used in the last calculations we did. So I'm just going to go ahead and rewrite them because they are the same since it's under the same pressure. However, the quality will be different. And the quality will be different because the specific volume is different in state 3 than it was in state 2. But I'm just going to go ahead and rewrite everything so that we don't have to go back and forth into our tables. Great. So let's go ahead and find quality. V3 is going to be 0.841 minus 0.001061 divided by 0.88467. We get 0.9494, and then we plug it into this equation right here. When we plug it in, we get that U3 is equal to 0.9494 times 2529.49 kilojoules per kilogram plus 1 minus the quality, 0.9494, times 504.47 kilojoules per kilogram. After plugging everything in, we see that U3 is equal to 2,427.024 kilojoules per kilogram. Great. And then we plug in to our original formula because we're trying to find Q. So we know Q is equal to M, the mass, times the specific internal energy of state 3 minus the specific internal energy of state 2 plus the work. We know that the mass is 1 kilogram, so that's great. Plug that in. U3 we just found to be 2,427.024 minus specific internal energy of state 2, so minus 2,413.4564. All of this is kilojoules per kilogram times, plus the work of 1.2 kilojoules. Great. Kilograms cancel out, and when we get that Q is equal to 14.767 kilojoules. And this is the amount of heat added going from state 2 to state 3. Perfect. We're almost done. We found out the first Q. We found the second Q. And now our final Q from going to state 3 to state 4. We find that Q, and then we add up all the other Q's together, and we figure out the total amount of heat that had to be added to this system in order to get it to become a saturated vapor. So now we are analyzing going from state 3 to state 4. So going to state 3 to state 4. It's a closed system, so we can use the equation of Q minus W is equal to delta U. We rewrite because from state 3 to state 4 there is no moving piston, there's no moving parts. So we know that there is no work being done in the system, so we can go ahead and cancel it to 0 because we have no work. So we have that Q is equal to, and we're going to go ahead and say U4 minus U3. But since our tables gives us specific internal energy, we go ahead and rewrite even further and say that Q is equal to the mass times the internal and the specific internal energy at state 4 minus the specific internal energy at state 3. Luckily for us, we know U3. We found U3 in our calculations above. So essentially what we have to find now is just U4. We need to find U4. At state 4, it is a saturated vapor. When it's a saturated vapor, things become easier because we only have to look at the saturated vapor column. So this is the saturated liquid vapor. This is the saturated liquid column. This is the saturated liquid vapor column. And this is the saturated vapor column. So this is as well saturated vapor, saturated liquid vapor, and this is saturated liquid column. So since it's a saturated vapor, we only have to look at the saturated vapor column. Great. So saturated vapor, we know that this specific volume at state 4 is, well, yeah, saturated, the specific volume at state 4 is 0.841 meters cubed per kilogram. We don't know the temperature at this state, and we also don't know the pressure at this state, right? So let's go ahead and look for the UV. We don't have 0.841, but we do have 0.88573 and 0.79325, and then their corresponding UV, or their internal energies, would be 2529.49 and 2533.56. So since we don't have the tabulated value, but we do have a higher and a lower one, we can simply linear interpolate. It's not that hard. Linear interpolation. We have specific volume. We're trying to find specific internal energy. So we're trying to find, what we have is 0.8, oops. What we have is 0.88573. And then the number that we want is 0.841. And then our lower boundary is 0.79325. The higher or upper boundary for our internal energy, or specific internal energy, is 2529.49. We're trying to find this one. And our lower boundary is going to be 2533.56. The formula I use is the following. So Y2 is equal to X2 minus X1 times Y3 minus Y1 divided by X3 minus X1, all of this plus Y1. This would be like my X1, my X2, my X3, my Y1, Y2, Y3. Plug it in or program it into your calculator, or even online calculators can do it for you really easily. And I figured out that my Y2 is 2531.4585. So my specific internal energy is going to be 2,531.4585 kilojoules per kilogram. So that means that my U4, because it's a saturated vapor, and the reason we know that is because of what we did in part 1, is equal to 2,531.4585 kilojoules per kilogram. From state 3 to state 4, we can use the formula Q is equal to M U4 minus U3. We plug everything in. Mass was 1 kilogram. Specific volume, or specific internal energy of state 4 is 2531.4585 0.31.4585. The specific internal energy at state 3 is 2427.024. We found that already. And then there was no work, so we don't have to add work. And after multiplying all of that, we get that Q is equal to 104.4345 kilojoules. Great. And that's the heat added from state 3 to state 4. Perfect. So the total amount of heat added is going to be the heat added from from state 1 to state 2, plus the heat added going to state 2 to state 3, plus the heat added going from state 3 to state 4, and that's going to give us our Q total. So our Q1, 2 is this guy over here. Wait, yeah. It's going to be this one right here. Our Q23 is going to be this guy right there. And then our Q34 is going to be that one right there. So we plug all that in. So Q12 is 953.2565. And this is kilojoules, plus 14.76 kilojoules, plus 104.4345 kilojoules. We add all of that, and we get 1072.4586 kilojoules. And that would be our final answer. So that's how much heat was added to our starting piston cylinder arrangement of it being saturated mixture, and how much heat was added to that saturated mixture for it to become a saturated vapor. And yeah, that's pretty much it for this video. Good luck with your studies.